I want to look now at definite integrals. I'm going to start by reviewing how they're defined for real valued functions. Then, just like we did with the definition of the derivative, we'll see if it makes sense just algebraically to modify it for vector functions. And if it does, so that it's actually something that could be computed, then we'll take a look at, does it actually mean anything? Okay, so I've written up the definition for a definite integral for a real valued function here. If I'm integrating from a to b, f of x with respect to x. Again, remind us of what that means geometrically. That's going to be the signed area between the graph of the function and the horizontal axis, where we count area as positive if it lies above the x-axis and negative if it lies below the x-axis. So that's sort of what we're trying to calculate here. But here's how it's done. It's done by taking the limit of a Riemann sum. And I want to just walk through that process, because when you first learn integration, you learn how to take Riemann sums and how to take limits of Riemann sums. And then you learn all the shortcuts, and it's easy to forget that this is how things are originally defined. But essentially, this limit of a Riemann sum comes from a four-step process that we're going to see again and again this semester, because it's a really, really useful way of calculating things. So I want to just review what that process is. Okay, so I say it's a four-step process. The first step is to chop. So we take the interval along the x-axis from a to b, and we're going to chop it up into little pieces. Now, it's not necessary to chop things up into pieces that are the same length, but strategically it's often advantageous to do that just because it makes our calculations simpler. So I'm going to suppose that we've done that. We've chopped this up, we'll say, into n pieces whose lengths are just delta x. And we do that by creating these endpoints. We'd have x0, x1, x2, and then b, our rightmost endpoint, would just be x sub n. And the length of all these little subintervals would just be delta x. Okay. Now, of course, if we've chopped the interval from a to b into little pieces, that's going to induce a chopping of this signed area that we're trying to calculate into little strips of area, so that I can say the total signed area is just the sum of all of these little strips of signed area, where again it counts as positive if it's above the x-axis and negative if it's below. Okay. All right, once we've chopped it into little pieces, so we've gone from one big problem to a bunch of little problems, step 2 is we're going to approximate. So I want to approximate the signed area of one of these pieces. So essentially I've got something like so. This is sort of like what maybe one of these pieces here looks like. I've got a nice base of delta x, but the height of my shape is changing. Okay. Now, if the height weren't changing, if I had a constant height, I'd just have a rectangle, and I could calculate the area very easily. It would just be the base times the height. And if I allow heights to be negative, that would actually allow me to calculate signed areas. So we have this problem that the height is changing, and we're going to do what it turns out is an incredibly useful mathematical thing to do. Although I don't, as a general rule, recommend this as a life skill. It's called denial. So we say the height is changing. Oh, it'd be really convenient if the height weren't changing, so let's pretend it's not. So we're going to choose a representative x value, and we're going to just look at what the function value is there. We're going to find the height at that particular x value, and we're just going to pretend that we get a constant height over that entire subinterval, so that we would have a rectangle whose base was delta x, and whose height was just my function evaluated at this representative x value. Now, we usually call that x value xi star. Let me just talk through that notation really quickly. Okay. X because it's an x value. I because it would be in the ith subinterval. So if it was in the 5th subinterval, I would be 5. Okay. The star is there just to say we don't necessarily have to choose the right endpoint. when we partitioned the subinterval, we generally used x0, x1, x2, etc., for the endpoints. And so xi would be the right endpoint of the ith interval. I don't necessarily want to have to use that, so that star here just says any point in the ith subinterval is good enough, doesn't necessarily have to be the right endpoint. Okay, so we approximate the signed area that we get. And you can see this is what we're adding up right here. This is the signed area that we have over the ith subinterval. And then step 3 is we add them up. And of course, when we add, we get the sum as I goes from 1 to n of f of xi star times delta x, and we call that thing a Riemann sum. So it's just a sum of signed areas of rectangles that approximates the value of our definite integral. Okay. So those 3 steps allow me to approximate a definite integral, and then step 4, we take a limit. So that's what we've got here. You'll notice we're taking here the limit as n goes to infinity. It's not actually important that I have lots of rectangles. It's important that I'm shrinking these bases to 0. That's what allows us to get away with that denial that we had earlier on, where we sort of pretended the height didn't change. Okay. If we shrink the base smaller and smaller and smaller, we're giving the function less wiggle room. It's going to wiggle a little bit less. So the error that we get from evening out the heights, that error is going to shrink to 0. So n going to infinity is not necessarily always enough. But if I've used the same delta x for each piece, my delta x would just be the length of the interval divided by n. Letting n go to infinity is going to make that go to 0. The fact that the base goes to 0 is what's actually crucial as we work with this. Okay, so that is a very quick review of how we define definite integrals. So they're the limits of these Riemann sums. So what I want to do now is say, does it make sense to generalize that to a vector function? So if I had the integral from a to b of r of t dt, it would have to be dt because my input variable is the parameter t. Does this make sense to talk about the limit as n goes to infinity of the sum as I goes from 1 to n of r of ti star times delta t? So let's see. I could certainly evaluate my vector function at representative points. Delta t, that would be a number. That would be a short time interval. So this is really just a scalar by which we're multiplying this function. So generally when we've got scalars and vectors, we would write the scalar in front. I've written it at the end just to match what we had with our real valued functions, but it would be totally fine to rewrite this as the limit as n goes to infinity, sum I goes from 1 to n, delta t times r of ti star, and that actually makes a little bit more sense when I'm thinking of that as a scalar by which I'm scaling my vector. Can I add up vectors? Yes, I can. We've got vector addition defined. And can I take limits of vectors? Yes, I can. So, just from a purely algebraic perspective, it is possible to create a Riemann sum with our vectors and then to take the limit of that Riemann sum. Now, it's not going to mean an area, because with a real valued function, we can define it as the signed area, this would just be positive area here, between the graph of the function and the x-axis. X is our input variable. When we graph, we're graphing the x-axis. When I'm graphing r of t, I'm just drawing it here in 2 space because that's easier to draw. If this is r of t, I'm not drawing the t-axis. It doesn't make sense what area I might be talking about. Now I can certainly create lots of areas using this curve as part of my boundary, but I can't create the area between this curve and the t-axis because the t-axis is not part of my picture when I'm graphing the function. So the notion of signed area is not what we're going to be calculating. We will be taking a limit of a Riemann sum, but the Riemann sum isn't going to be representing areas. It's going to represent something else. So what I want to do is I'm going to end this video now. In the next video, we're going to take a look at an example of a Riemann sum created with a vector function and see if we can make sense of what that means and what it is that we're trying to calculate.